Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our graphical application of the fundamental theorem of calculus, part 2. Dun, dun, dun. We're given a function, g of x, that's defined by an integral. We can think of that function g as an area accumulator. We can start at that lower limit, in this case x equals -2, and determine how g's function values change based on how much area is accumulated as I scan from -2 up until whatever x value of concern I'm asked about. And so to find g of -2, that's as easy as starting at x equals -2 and scanning towards the upper limit, in this case -2, and seeing how much area we accumulate. Well, because no area can be accumulated if I don't scan to the left or to the right of my starting value, then this is automatically a 0. That is an x-intercept of my function g. No area can be accumulated if I scan from -2 to -2. So if I were to show this actual evaluation where I simply substitute in my x value of concern, -2, into my function rule, just like we did in middle school, except now we have a function rule that has an integral in it, right? Then I can see that from -2 to -2, the value of that definite integral is 0. So I'll go ahead and write that once, -2 to -2. Starting at -2 and scanning towards -2, I can't accumulate any area, so the value of this definite integral is 0. Raise your hand if you had that. So you have 0 for the first one. Good. That's automatically an x-intercept. That lower limit in my integral defined function g is automatically an x-intercept of the graph of g. All right, let's go ahead and consider g of 2 then. We'll do the same thing. We'll evaluate g of 2 by substituting in 2 for my x value, my independent variable value in my function definition. So what would that look like if I were to write that initial substitution? Well, from -2 up until 2 f of t dt, bless you. And I can evaluate that definite integral graphically. I'll interpret that as the area accumulated as I start at x equals -2 and scan up until the upper limit, in this case +2. So I'll be scanning from the left to the right, so my usual interpretation of area accumulated will apply. That is, area above the x-axis will count as a positive contribution, area below the x-axis will count as a negative contribution to my overall value of the definite integral. And I'm counting up units. So I'm getting 1, 2, 3, and then -1. -2, -3. By golly, it looks to me like this positive contribution is canceled out by an equal and opposite negative contribution. So it looks to me like 0 is what I'm getting. Raise your hand if you had 0 again. 0 again, but for a different reason, right? This also is an x-intercept of the graph, right? It's my next x-intercept of the graph. Interesting. We'll see how this plays out now as we look at the second part of that first page on your note sheet. But first, let's do g of -6. So g of -6 says start at -2 and scan up until the upper limit. In this case, -6 is scanning from right to left, and consider the area accumulated, right? And how that changes my function values of g. So now we're starting at x equals -2. We're scanning towards my upper limit, x equals -6. In this case, that's scanning from right to left. For the opposite interpretation will apply. Area above will count now as a negative contribution and vice versa. Let's scan all the way to here. If that were an x-intercept is what I intended of the graph of f, then this would be 1, 2, 3, 4, 5, 6. But it's scanning from right to left, so it's going to be -6. Raise your hand if you had -6 already. So we had -6. Awesome work, you guys. That's great. What questions do you guys have about the first three? Okay, then we still have 4 and 5. G of 1, right? G of 1, this is gaining another point for us for the second part. We'll start at -2. We'll scan until the upper limit. We'll count positive contribution 1, 2, 3. We'll take off negative contribution of 1, and we're back to 2. Is that what you guys are getting to? So I'm going to quickly write that just for our notes. -2 to 1. Of f of t dt graphically gives me +1, +2, +3, -1 is 2. Raise your hand if you have 2 for number 4. Do you have 2 for number 4? You guys are doing great. Okay, so we got the graphical application of fundamental theorem of calculus part 2 taken care of, so long as we're evaluating my given function. My function g, right, was given by the integral defined expression. I simply substitute my x value and evaluate the definite integral graphically by counting area. No problem. What happens if we're dealing with derivative values? fundamental theorem of calculus, part 2, says that differentiation and integration are inverse processes. And so if g is given by the antiderivative, right, the antiderivative of f, then g prime must be given by my original f, with the key difference that now my independent variable was substituted into the integrated function. So the fundamental theorem of calculus says, if g of x is given by the integral from any constant up until x of an integrated function, a little f of t, then g prime of x is given by f of x, that integrated function, right? Differentiating both sides would get me g prime. Differentiating the right-hand side would undo the integral and get me right at that inner function, the integrated function. But now I've got the x in there. You can think about why we have x in there again. Remember, we started out doing this the long way, right? The long way was find an antiderivative for little f and evaluate it in accordance with the fundamental theorem of calculus part 1. If we could find an antiderivative for my original function, little f, I'd call it big F. I'd plug in the upper limit, big F of x. I'd plug in the lower limit, big F of negative 2. I'd subtract the 2. So I'd big F of x minus big F of negative 2. If I now differentiate that to generate g prime, I'd differentiate big F of x minus big F of negative 2. What's the derivative of big F?
Big F prime?
Yes, right? Little f, right? We decided that my antiderivative was big F, which means that my derivative of big F gets me right back to little f of x. Minus, what's my derivative of big F at negative 2? Well, I don't know what big F it is, evaluated at negative 2, but I know that it's a constant. And what's the derivative of any constant? 0, leaving me with that original f of x. And so, right, you should be able to do that the long way. If you had some easy function there, you could evaluate that definite integral with an x in it and then differentiate it to get this. All right, let's go ahead and finish that out then. G prime of 5 is the same as g prime of 5 equals f of 5. So g prime of 5 equals f of 5. Can I get f of 5 from a graph? That's as easy as getting the y-coordinate of my function value f, whose graph is shown when x equals 5. So I'll go right here. I'll grab the y-coordinate, and it's not undefined. Does not exist. It's not DNE. This is simply the y value of the function f shown, and that's 3. Isn't that 3? Raise your hand if you have 3. So anybody have 3 already? Hey, that's great news. Woo! Math works. Love math. Seriously. All right. So now what I wanted to do is take the same graph but do some different things. And so let's practice with some primes, some double primes, and ultimately let's use, right, this function definition to sketch a graph of g. And we'll even do it on the same axes so we can kind of review some of those connections between a function and its derivative. So here we go. G prime of 2 then, new exercises, but we're still starting at negative 2. So I'm going to start at negative 2. I'm going to scan towards the upper limit. No, I'm not. Is this g prime? Oh, g prime of 2 is even easier. If g is given by the integral defined expression, then g prime of x equals f of x. And so g prime of 2 is the same as f of 2. Can I get f of 2? Certainly I'll go to my graph and I'll see what y-coordinate is returned by my function f when x equals 2. That appears to be negative 2. Is that what you guys are getting? Negative 2? All right. G double prime of negative 3. Well, the fundamental theorem of calculus didn't say anything about double prime, the second derivative of g with respect to x. Well, no, but I know that g prime of x is given by f of x. Therefore, one more step down the ladder would get me to g double prime. This means that g double prime must be given by f prime of x as I step down the ladder one more rung. So, g double prime of negative 3 is the same as f prime of negative 3. And this is asking me for the derivative of the graph of f when x equals negative 3. And we can interpret that in our usual sense. If I'm talking about this graphically, then the slope of my original graph f when x equals negative 3, bless you, would be the derivative of f. And so it looks to me like this is part of a horizontal line segment whose slope is what, Colin?
0.
0, absolutely. Raise your hand if you already had 0 for number 2. Did you guys get there already? Good job. Okay. And g double prime of 3. G double prime of 3 puts me at f prime of 3. and f prime of 3 would be the slope of my graph f is shown when x equals 3. And so we're talking about the slope of that point, right? The slope of that point. And when you say the slope of that point, then you should have all kinds of red lights blinking in your head, right? Sirens, danger, danger, red alert, red alert. This is Max and Ruby, Ruby and Max. Classic PBS, love it. This is
just on, now that shows, I believe it's on Nick Jr.
Nick Jr. Nice, Nick Jr. That's what I'm going to call him. Nick Jr. Love it. So this is undefined. How come? Well, it's a cusp, right? There's an abrupt change in slope. The left-hand slope values don't match the right-hand slope values. Therefore, the overall slope at that point, or the derivative value at that point, is undefined. Does not exist. So this is undefined. It doesn't equal anything. Oh, I don't know what happened there, but it's undefined. It's undefined. There's a cusp, an abrupt change in direction, right? And so the overall derivative value does not exist. It's undefined. Awesome. What questions do you guys have on these 1, 2, 3? Then finally we get to try and make a picture, right? What does F, don't turn on, what does G look like? And so we've gone ahead and we've evaluated several y coordinates on my function G by direct substitution. So let's go back to our earlier Bellwork and let's see if we can't get a picture here. So in our original evaluation, we had various, bless you, we had various x values, and we get a whole slew of them for our Bellwork. So what do? We did -2, 2, -6, -2, 2, -6 we did too. What else did we do? We did 1. Oh, we got another one. So we did 1, okay. Great, so we got all those for free. So, in our first one we did -2, 0, 2, 0, -6, -6. Let's go ahead and import that. And what was G of 1? We did G of 1 and that was 2. Alright, so let's see if we can't plot these points and begin to construct a graph of my original function G that's given by the integral expression, the integral of f of t with respect to t. So here we go, -6, -6 on the point. -2, 0 is a point. 2, 0 is a point on G. On G, blue G. We're making blue G. 1, 2 is a point. All right. For some reason, I'm not feeling like I have enough points to make a sketch now. So we could start at -2 and start accumulating area if we wanted to, right? And then we can finally remember our connection between a function G and its derivative, G prime. We know that when my original function's increasing, then G prime is positive, right? And so on and so forth. And so I think that's going to help with us to fill in our final points. So here we go. If I start at -2 and I scan towards -1, I would be adding on 2 units. And so it looks to me like G of -1 would be 2. If I continued scanning from -1 till 0, I'd be adding on another 1 unit. So I know, in fact, that G of 0 equals 3. How come? How come? Well, because I'm starting at G of -2 is 0, and I'm accumulating area as I scan from left to right, and in the process, I'm adding value to my y coordinates of G. How much value? Looks like I'm adding 2 units of value in the process of scanning from -2 to -1. I added on 2 y coordinates to my y coordinate of 0, my x-intercept value. So what's my y coordinate 0 plus another 2? 2. Still scanning. Still above the x-axis. Still making a positive contribution towards my function values. How much? 1/2 times base times height. This is a little triangle whose area is 1. So I need to increase my y value by 1 in the course of scanning from -1 to 0. I went up from y coordinate of 2 up until y coordinate of 3. Yes? The entire time my function here was above the x-axis, right? My f of t was above the x-axis, that's G prime. My functions of G were increasing, right? They were increasing. Let's keep going. So here I am at 0, 3. Oh, here I am at 1, 2. Oh, here I am at 2, 0. So I've got a pretty good indication what this is doing. Let's keep going. In the process of going from x equals 2 to x equals 3, I have now lost 2 y coordinates. How come? Right? Because the derivative of g, that is f, whose graph is shown, is beneath the x-axis, and we've accumulated a -2 area units. And so this needs to go down to, what, here? How's that? Awesome. And then this one, as I go from 3 to 4, right, as I go from 3 to 4, is almost, it looks like this is a point here, so gosh darn it, that's not exactly 1. It's going to be a little bit less than 1 down. And this is going to be a little bit more than 1.5. Okay. So I just need a little bit in here. So let's go ahead and go backwards now and see if we can add a couple more. As I start at -2 and I scan from the right to left, this area above 2 units is going to be subtracting off 2 y coordinates from the value of g. How come? Because I'm scanning from right to left. And so this 2 area units now are interpreted in the opposite manner. They're going to be a negative contribution to my function values. So from y equals 0, I'm going to have to go down 2 units in the course of scanning 1. Oh, another down 2 units. And then another 1.5 units as I go from -4 to -5. That's down 1.5. Okay. Here we go. Ready? Let's do it. We're now going to sketch in an estimate for my graph of g. If my function f, which is g prime, if my function f is increasing at a linear rate, right? That would be degree 1 positive. That means I have what shape? Well, I would be degree 2 positive, which is right side up bowl shape. Can I make a right side up bowl shape up until x equals -4? Certainly. In between x equals 4 and x equals, -4 and x equals -1, g prime, which equals f of x, is positive, right? Positive constant, right? That means the original graph, g, would be, well, increasing in a linear fashion. Can I fill that in? Yes, certainly. In between x equals -1 and +1, g prime equals f of x is decreasing in a linear fashion. That means the original g would be what degree? 2, but negative, upside down. Can I draw an upside down degree 2 polynomial for this portion of the graph? In between x equals -1 and +1? You bet your boots. Oh yeah. In between x equals 1 and x equals 3, g prime equals f of x is negative constant. That means that the shape of my original graph g would be what? Linear decreasing. Can we draw that in? You bet. So from here to here, I need linear decreasing. In between x equals 3 and x equals 5, g prime equals f of x is linear increasing, which means that g, my original function, would be degree 2 right side up. Can I draw that? And, oh, got a little carried away there. And in between 5 and 6, g prime equals f of x is positive constant, which means this is linear slope 3. And then this is just a guess. Right? This is a guess. I want to see how we did. I'm dying to see how we did. For printing. How do you do? There we go, there we go, there we go, there we go. I think we did okay. Hey, that's pretty good. Not too shabby. Not too shabby for a first hour hump day, Wednesday, after staying out late shoveling. Gosh, that was heavy some last night. I don't know who's in charge of shoveling at your house. Tell you what, walking sideways down the hallway this morning. All right, so let's go ahead and take care of our OTL number 6. Guys, we've got to staple our worksheet, our integral practice worksheet, along with the book problems. So I don't care which is on top, so long as your infinite canvas score, your name, and OTL number 6 are clearly on top. Once again, infinite canvas score will be gained today by taking the number you complete out of 42. That includes your integral practice worksheet. Divide, enter, multiply by 2. Let's box that infinite canvas score nice and big. Again, it doesn't matter what's on top, but it does matter if you have it stapled with your worksheet.
They got it.
Yeah.
So let's go ahead and take a look at what's in tap for our review day. And now it's that special time again. No Riley. Not that special time. Or that time, Riley. Classic Riley joke. Riley cubed. It's time for the elevator game. Oh my gosh, have we played the elevator game before in here? I don't think we have. So the elevator game, also known as going up or going down. Ding! The elevator game works like this. First things first, we need our new classroom numbers because we've got new rosters. It's second semester, we've got new classmates. And so everybody get ready because we're going to number off. We're also going to make sure that we include tests in our numbering. So here we go. We're starting with Kobe. Get ready and then write your number down inside your binder, right? Or tattoo it on the inside of your forehead so you can just look up and remind yourself what it is. Here we go. Kobe, your number, obviously. Brandon?
4, 5, 6,
8.
Tess is 11.
12,
13, 14,
17,
19,
20.
20.
And we're 1 to 24. Everybody write down your number now so you don't forget. 1 to 24. I'm going to use the random number generator. If you want to get your little derivative sheet or your antiderivative sheet ready, you might have guessed now the ladder game refers to which rung am I on. I'm going to differentiate an expression, or I might integrate an expression. That is, go down one rung on the ladder or step up one rung on the ladder, depending upon which one you're asked to do. And so once again, if you'd like to have your derivative sheet present, you may. Of course, I know all the cool kids are going to do it from memory because you memorized with your flashcards at Subway, with your Ziploc baggie in there. Let's do it. Assume all derivatives and antiderivatives are with respect to x. So we'll just assume that all derivatives and antiderivatives are with respect to x. Okay, here we go. Round 1. Sine of x. And we want the derivative, sine of 3x. Okay, we're going to find the derivative with respect to x. And we're going to find the antiderivative with respect to x. So get ready. We are 1 through 24. First we'll go derivative. Everybody get ready. Derivative. Number 3.
3 cosine 3x.
3 cosine 3x. Raise your hand if you agree with Riley. 3 cosine 3x is correct. Good job. Sine differentiates the cosine, then times the derivative of the angle. Nice work with the chain. Everybody get ready. The antiderivative going up the ladder or the elevator. Number 6.
Negative 1/3 cosine plus c.
Negative
Cosine 3x.
1/3 cosine 3x plus c. Raise your hand if you agree with Courtney. Negative 1/3 cosine 3x plus c. Nice job with the constant, and thank you for remembering the constant integration whenever finding an antiderivative. You win. Plus 10,000 points. Don't even bother coming back to school the rest of the semester. You're basically guaranteed an A. Good job. Next, derivative of e to the 4x. Get ready. E to the 4x. Get ready. Number 11.
Test.
Did you pass?
No, it's test.
Oh, it's test. Like, don't pass. Don't pass. Number 10.
4e to the 4x.
Hang on, let me process here. 4e to the 4x. Raise your hand if you agree with Tyler. 4e to the 4x is correct. It's the exponential itself. times the derivative of the exponent, and then times the natural log of the base. Base e exponential is the log of the base. Natural log of the base is 1. So 4e to the 4x. Good job. Get ready. The antiderivative going up the elevator one floor. Get ready. Number 8.
1/4 e to the 4x.
1/4 e to the 4x
Plus c.
plus c, thank goodness.
Plus c.
We don't have to make any ribald comments about Kyle's inability to include the constant integration. I'm glad you did. Okay, everybody, raise your hand if you agree with Kyle's antiderivative. Do you agree with Kyle's antiderivative? Good job. That's absolutely right. We know we need a 1/4 to account for the fact that it's not there, right? It's not there. And so in accordance with the chain rule, we multiply by the derivative of the exponent 4, and that would times the 1/4 give me the 1 in the original. Good job. Get ready. The derivative of e squared. The derivative of e squared with respect to x. Number 7.
0.
0? Raise your hand if you agree with Riley. Cursive. Yes, it's 0. E squared is just a constant. It's about 7.34 something. So the derivative of any constant is 0. Nice job. What about an antiderivative? So an antiderivative with respect to x for e squared. Antiderivative with respect to x for e squared. Number 12.
Would that be x times e squared
Yes, e squared times x
plus e?
plus c. Raise your hand if you agree with Emily. So e squared x. Good. That's the same as the antiderivative of 2 with respect to x would be 2x, right? That constant multiplier. Good job. Next, the derivative of e to the negative x. Get ready. Number 2.
Negative e.
Negative e to the negative x. Raise your hand if you agree with Megan. Negative e to the negative x. Good job. My derivative of the exponent in this case is the negative. An antiderivative. Get ready. An antiderivative for e to the negative x. Number 17.
Negative e to the negative x.
Plus e. Raise your hand if you agree with Evie. Negative e to the negative x. Could it be? Could it be? Yes. Our derivatives and antiderivatives of exponentials base e are cyclical, right? That's why we choose to work with natural logs and base e exponentials whenever possible in calculus. Nice job. Whoa. Let's throw some harder ones. If you need to jot something down on a piece of paper, that's fine too. Don't be shy, but I will be calling on you momentarily. So the derivative of natural log of x over x. And it doesn't have to be fully simplified when you give it to me, right? I'm going to write down what you say, and without saying whether it's right or wrong, and then we're going to go ahead and poll the class. So what would a derivative, the derivative of natural log of x over x look like, right? Number 16.
Like
You can do it in parts, yeah.
1 over x times x to the negative 1 plus ln of x times negative x to the negative 2.
Are you done?
I don't know how to look at that.
It's all right. So I'm thinking that you in your head. This is my think bubble.
Did ln of x
You did ln of x times x to the negative 1. So it looks like Maggie's doing the product rule. Let's see how the product rule went then. So the derivative of a product of two functions is the derivative of the first times the second, right? Plus the first times the derivative of the second. The derivative of the second would be exponent times the base raised to 1 less times the derivative of the base. Raise your hand if you agree with Maggie's derivative. Good, good, absolutely. Now this should be able to look like the same as if we had used the quotient rule. And so let's go ahead and do the quotient rule in red, right? This is good practice. What if we had done the quotient rule? The quotient rule applied to the original would be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. What's that? Okay, so are these two equivalent? Well, this would give me, I better do green. This would give me 1 over x times 1 over x is 1 over x squared plus ln of x, oh, minus, that'd be minus, can I do this? Oh, look at that. Minus ln x over x squared, which would be 1 minus ln x over x squared. Does that equal question mark? 1 over x times x minus ln of x over x squared? Yes, because this is just 1 minus ln x all over x squared. Yes? Math works. Going up. Ding! Antiderivative. Get ready. Gonna call on you. Getting out of your seat doesn't mean that the calculator is not gonna call on you. Number 4.
That would be me. It would be, I just had this, ln squared of x over 2 plus c.
Raise your hand if you agree with Brandon. ln squared of x over 2 plus c. 3, 4, 5.5. 4. Non-committal. 4.5. 4.5 in a 4 and 3/4. 4 and 3/4. 5, 6, 7, 8, 9. You're right, Brandon. What's going on here? Well, this 1 over x is acting as the derivative of ln of x, a quantity on top to the first power. I would utilize the power rule. So long as I have the derivative of the base in this power function, which we're calling ln of x, and I do, the derivative of ln x is 1 over x, I can simply add 1 to the exponent and divide by the new exponent. So Brandon recognized this as a power function, base to the exponent, where the quantity ln x was my base, and my exponent currently was 1. So I need to add 1 to the exponent and divide by the new exponent. Nice work, Brandon. Next round. Ooh. Derivative tangent x. You don't need any more time. Enough talk. Number 22.
Secant squared x.
Raise your hand if you agree with Hayden. Secant squared x. Secant squared x is correct. Good job. Antiderivative for tangent of x. Oh, gotta have it memorized. Number 3.
Negative natural log of absolute value cosine of x plus c.
Raise your hand if you agree with Riley. Good. Alternate could be written as, who knows the alternate form? What else would that look like? Michael?
Secant, or regular natural log, absolute value secant x.
Nice job. Absolutely. So either of those are correct. You could use either one on your test coming up next class. All right. Awesome. What questions do you guys have about tangent of x? Then let's do another round. Secant of x derivative. Get ready. Number 6. Derivative.
Secant of x times tangent.
Nice job. Secant x times tangent of x. Good, that's correct. I'm not going to pull the class because we all know about that. What about antiderivative going up? Get ready. An antiderivative for secant x with respect to x is number 13.
Natural log of absolute value of secant x plus x plus c.
Raise your hand if you agree with Colin. You're so correct. Good job. Way to go, way to go, way to go, go, go. And last round. Derivative of negative 2 cosine of 2x. Get ready. And the derivative is number 15.
Is it negative 4 sine? No, positive 4.
I don't know. We're going to pull the class. We're going to pull the class. Raise your hand if you agree with James. Positive 4 sine 2x. Positive 4 sine 2x. Let's check. Negative 2 times cosine differentiates to opposite of sine. So opposite of negative 4 gets to the positive. Goes to sine and then times the derivative angle. 2 goes to 4 then. Absolutely. Nice job. Antiderivative. Final question. Get ready. Antiderivative. We're going backwards. What would it be? Number 1.
Negative sine 2x.
Negative sine of 2x plus c. Nice catch. Raise your hand if you agree with Kobe. Negative sine of 2x plus c. Okay, so if we differentiate this, we get negative. Sine of 2x goes to cosine of 2x, and then times the derivative of the angle would be 2, and that gives me the negative 2 cosine 2x. Nice job. Way to go, you guys. So today, you're going to have in-class work time to address the concept and skill guide that you just picked up. There are review problems. It's on a separate page, and so the review problems that go along with the concept and skill guide are your OTL number 7. Those will be collected, right? Those will be collected as your review OTL number 7. So what do we need to look for on our Unit 6, right? Our Unit 6 test. We want to make sure that we're comfortable applying the fundamental theorem of calculus part 2 graphically, as well as algebraically. We want properties of logarithms, logarithmic differentiation, you guessed it, L'Hopital's rule, regardless of spelling, and then derivatives and integrals of transcendental functions. Remember, that's my exponential functions, my logarithmic functions, and my trigonometric functions. I'm going to go ahead and stop the recording now and save it. I want you to know that you may work with a partner or you may work individually. You don't have to.